Hello Science 30s. In this video we're going to be looking at energy mass equivalency, or that famous equation E equals mc squared. Now you may know that formula came from Albert Einstein back in the early 1900s and has to do with his theory of general relativity. Now I just grabbed this from the textbook because I think it's a good thing to look at, and I like the way that it's worded. So the idea is a pellet of uranium used in nuclear power plants has a mass of about 7 grams. If you can think about what 7 grams is, that's less than 2 teaspoons of sugar. But that same amount, energy, that it can release is the same as 3.5 barrels of oil. So that's 550 liters of oil, 480,000 liters of natural gas, or 807 kilograms of coal. And so the question is, how can such a small pellet of uranium be such an enormous source of energy? Now, guys, when we talk about this E equals mc squared, we have to think back to our alpha, beta, gamma radiations, and then think about nuclear fission, and each one of those is going to release a different amount of energy. And so like the alpha and beta, for example, they use alpha and beta radiation to power things like space probes, but it cannot power anything like a city. You need to get into the nuclear fission reactions in order for that to happen. So the idea is that this 7 grams right here, this 7 grams of uranium, that mass is actually converted into an energy. So what we can do is we can take, if we go with that assumption, then we go with the assumption that mass can be turned into energy. So mass can be turned into energy. Then what we can do is we can take the mass before and after a nuclear reaction, and we can find out how much of that was converted into energy. And so again, we go back to your data booklet, and there's the formula. So once again, guys, we always write it as E. Well, often, I mean, you see this in everyday life, E equals mc squared, but in fact, it is not E equals mc squared. It is delta. E is equal to delta mc squared. And so what we need to do, delta, of course, means change. And that is really important when you're writing the formulas for class, okay? Always include that delta. So change in mass then can lead to a change in energy. And so again, we're just going to now jump right into an example. So what I'm going to do is I'm going to do this example here, and I'm going to use this table right here, which is in your data booklet. And you need to be using this table as well when you're doing these questions. What we're looking at here now, so before we used this, when we were looking at, okay, here's the alpha particles, here's the beta particles, and here's the gamma radiation right there. Now what we're looking at, though, is the mass. And what's really important to realize here about the mass is this is 4.00151. That would be the mass of a helium, but it is times 10 to the negative 3 kilograms per mole. And so this is not this number is correct, but it's times 10 to the negative 3. And again, you've just really got to be organized when you set up these questions, because it's a lot of paperwork, a lot of work that there are easy ways to kind of screw up. Okay, so just take your time, guys, when you're doing these questions, both when you're practicing them and when you're doing them for the questions that I assign for homework as well, okay? All right, so let's get into this question, and I'll show you how to do this. So the fission of uranium-235 that occurs in a CANDU reactor involves the following reaction. And there we are, there's our reaction right there. And we'll be using that right away. So calculate the change in mass between the reactants and the products for this reaction and the corresponding energy change. Okay, so first of all, we've got to realize that there is an arrow, and this arrow is going to split up your reactants from your products. And so here are the reactants, here are the products, and the difference in the mass between those is going to be your delta M. So if we were to get a formula for that, that would be delta M is going to equal the mass of the reactants minus the mass of the products. So that needs to be our first step, is we need to figure out the mass of the reactants. So let's do that right now. So the mass of the reactants is going to equal, our reactants in this case is going to be the mass of the uranium plus the mass of that neutron. So this is going to equal the mass of the uranium. So now what we do now is we go over here, and it's not just uranium, it's uranium-235. Now in this case, there is only one uranium listed, and that's uranium-235 right there. And so that would be your the mass, so 235.0 blah 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 blah. Okay, so go back to here and let's write that down. So that would be 1 mole. There's only 1 mole. Keep in mind, guys, we are still watching for coefficients. So coefficient in front of this uranium right here is a 1. The coefficient in front of this this neutron right here is a 1. The coefficient in front of this neutron here is a 3. And so that's really important to realize. Coefficient here of 1 in front of this barium-141, and then a coefficient of 1 in front of that krypton-92 as well. So we're always going to include the mole in this. And you notice that in the units even. The units don't make sense unless you include this. And so we have 1 mole multiplied by that 235 point, and I have it written down here, so it's 0.4392. Now that is times 10 to the negative 3 kilograms per mole. So moles will cancel out here, and you'll see we'll be left with kilograms. Now that's just the mass of the uranium. We also need to add to that the mass of that 1 neutron. So there's 1 mole of that neutron, and then we're going to times that by the mass of a neutron. So once again, we would go over here. I'm not going to do this anymore. I'm going to just write it down after this. But we would go down and we would find the neutron mass right there. Okay, here's our neutron, and then there's the mass. And so we'll just, again, I'm not going to go back and forth anymore, guys. I'll assume you can do that. And so now what we're going to do is go 1.00866 times 10 to the negative 3 kilograms per mole. So once again, we see the moles cross out, and our difference in mass, our mass of our reactants here is going to be 236.05258 times 10 to the negative 3 kilograms. Now, you're going to either want to write that down, or you're going to just keep that in your calculator. I mean, people who are adept at using their calculators, you might be able to do all of this whole thing in one fell swoop on your calculators. That's really up to you and your comfort level. Okay, so then we have our mass of our reactants. So the next thing we need is the mass of the products. So let's get that done right now. So we have the mass of the products is going to equal. So our products here are going to be 3 things. First of all, we have 3 neutrons, plus we have the mass of the barium, 141, plus we have the mass of the krypton, the mass of the krypton, and that krypton is krypton-92. Okay, so now again, I'm going to assume that you guys can go over and find out these masses yourself from that table. So I'm just going to go ahead and just show the work here now. So this would be 3 moles of a neutron, and our neutron, we already looked that one up, was 1.00866 times 10 to the negative 3 kilograms per mole. So you see here now, of course, you're going to multiply that 1.00866 times 10 to the negative 3 by that 3. Okay, now we're going to have the krypton, or sorry, first of all, we're going to the barium-141. So the barium-141, if we go over to that chart to in your data booklet, is going to have a mass of 91.0 where are we at here? 91.92611, and this is times 10 to the negative 3 kilograms per mole. So once again, moles cancel out. And we have one more addition here, and that's the mass of the krypton or the barium. I'm not even sure what order we're in here now, but this would be 1 mole multiplied by 140. I guess this is the barium 141, obviously. So that would be 140.91441 times 10 to the negative 3 kilograms per mole. Moles cancel out, and we are left with so our mass of our products is going to be 235.866.5, or not 0.50, that doesn't make any sense, 50 times 10 to the negative 3 kilograms. Okay, so now we have the mass of the reactants. Mass of the reactants is right here. I'm boxing this even though it's not a final answer, but just to show you what we have. There's our mass of our products. So now what we need to do is figure out the delta M. And so the delta M is going to equal mass of the reactants minus mass of the products, which is going to equal 236.05258 times 10 to the negative 3 kilograms minus the mass of the products, which is 235.86650 times 10 to the negative 3 kilograms. And we land up with a difference then of our delta M is going to be, where are we at here? This is going to be 1.8608 times 10 to the negative 4 kilograms. So that's a very, very small difference in mass from that uranium. Your uranium started off pretty, started off really, the difference is really small. Let's put it that way. It's under a gram. Now we need to figure out what difference of energy there is. And so that's where the E equals mc squared formula comes in. So we're going to take this delta M and we're going to put it into that formula and figure out what a change in energy it would lead to. So our delta E is going to equal our delta mc squared, which is going to equal our delta M, which is 1.8608 times 10 to the negative 4 kilograms. And we are going to be multiplying that by the speed of light, which is 3.00 times 10 to the 8 meters per second, and that is squared. So you notice the units here land up being a kilogram meter squared per second squared, which is the same thing as a joule. And how many joules do we land up with? A lot. 1.67 times 10 to the 13 joules of energy. Now, of course, they're going to take that energy in the CANDU reactor, and they're going to use that to boil water. That energy is going to be largely be released as heat. So they're going to take that, they're going to boil water, and they're going to put that through a bunch of high pressure pipes, which is then going to be piped into a turbine, which will create the kinetic energy that we need in order to make electrical energy. And that's going to be your homework for this week, guys, on mass energy equivalency. E equals mc squared. You are now all as smart as Einstein. Have a good week.